Hello, my fastidious physics students. Right now we're going to be looking at planetary motion. So planetary motion is a cool concept, and the background on it goes all the way back to a guy named Tycho Brahe, who took very detailed sort of charts of the night sky and the path of the planets through the stars. And his whole life he just charted these things, but his charts were so good that a guy named Kepler, who came after him, was able to use those charts and come up with mathematical relationships between the planets. So his relationships sort of look like this. He developed the three laws based off Brahe's charts, and those three laws were this. He found that the planets move around the sun in an elliptical shape. So that's his first law. So the first law is this idea of ellipses. And so an ellipse, the characteristic part of an ellipse is that it has two focuses. And so we would say that the sun is at one of those focuses. Now the second law is sort of illustrated here with this drawing or this graphic. And so the second law says that as a planet is closer to the sun, it'll tend to move faster. So you'll see that this has has covered more distance than this has. But if you were to draw imaginary lines here for the radius, you'd notice that these ones are longer. So if you take the area of this and the area of this and you compare them, they end up being equal. So that was his second law, that even though it moves faster here, the area that it covers is equal. So if you were way out here, you would have this tiny little bit covered, but if you were to draw that, that would also be the same area, and it would equal this, it would equal that. That's the second law. Now the third law, he was able to relate this idea of period of going around the sun and distance away from the sun in this equation, where he said that the period of one planet divided by the period of another planet squared equals the radius of that one planet, or the distance from the sun divided by the radius of the other planet cubed. And so this relationship here allows us to figure out a little bit about other planets, given some information about one of them, so you can figure out all sorts of cool things. So let me show you a couple of examples of this. Here's an example right here, where we would say that let's go ahead and look at this right here. We would say that what if we had a star and we had two planets going around that star? Here's planet A and planet B. So what if we knew something about each one of those planets? So what if we knew their period, the amount of time it took them to go around? Say this one was 1.8 years and this one was 7.15 years. So if we knew the radius of this one, we could figure out the radius of that one by just plugging it into Kepler's third law. So you notice the time of A divided by the time of B squared equals the radius of A divided by the radius of B cubed. So go ahead and if you solve that, you'll find that this equals 15.8 right here. And so to get rid of the cube root, or the cubed right here, I could take the cube root of this and then multiply by 4.2, and that's going to equal the radius of A, which, let's see if we calculate that out, happens to be 10.53 units. So that makes sense. So 10.53 units right here would be the distance here. So if this is 7.15 and this is 1.5, so that distance, and then that seems about right. And so you know that there's a relationship between those two, and you can figure that out. Using even less information, we can do a similar type of thing. So what if we were to analyze a problem like, say, with the sun and the Earth going around the sun? Let's say we're going to look at an asteroid here, and let's say that the only thing we know about the asteroid is it's exactly 2 times the radius of Earth. Is actually what the asteroid here's radius is. We know it's twice as far from the sun as the Earth is. So we've got enough information actually here to figure out how long it will take this asteroid to go around the sun according to Kepler's third law. So let's see. We want to know the period of the asteroid. So let's call the period of the asteroid period of A. we know that the period of Earth going around the sun is going to be 365 days, right? And so if we take that squared and we set that equal to the radius of the asteroid, we know the radius of the asteroid is 2 times the radius of Earth, and the radius of Earth, of course, is the radius of Earth. So that right here is going to be cubed. I can cross-cancel that. 2 cubed is 8, so I could say that that is 8 right there. So that equals 8. If I wanted to get rid of this square right here, I could take the square root of 8, and I would multiply that times 365 right over here, and that would actually give me the period of A. So if I go ahead and take the square root of 8 times 365, I get, let's see, 1,032 days, about a little bit over that, but that's good enough. 1,032 days, or you could say 2.8 years. It would be how long it would take for that asteroid to go around the sun. So this third law of planetary motion gives us a lot of really neat ways to find out all sorts of information about another planet if we know something about a planet that's that's going around the same source. So this is very handy in looking at planets within our solar system, and we've utilized this a lot to figure out a whole bunch of these stats and facts about the planets in our solar system. So hopefully this helps, and we're just going to go ahead and add force and gravitational constant that Newton came up with in the next couple of videos.